I want to put my chain rule to use a couple of different ways. I think one of the most direct, talk about inverse functions. So when I talk about either the sine inverse, or as it's sometimes known, the arcsine function, what does that do? What does that function do? It undoes sine. So you give it a number between -1 and 1, and it tells you here's an angle whose sine is that value. And that angle is between -π/2 and π/2, either in the fourth or the first quadrant. But so mathematically, I can say that's the same as saying, oh, y is the sine inverse of x, the same as saying sine of y is equal to x. I know how to take the derivative of sine. I don't know how to take the derivative of the arcsine. So I don't know what to do over here, but I do know what to do over here. So if I want to find y prime, I can work with this equation, and I can use the implicit differentiation idea that we just covered. I take my derivative with respect to x. What's the derivative of x? That's easy. The derivative of sine of stuff, cosine of stuff, but wait, there's more. What's the but wait, there's more part? I can use that. I can use y prime, however you want to write it. There's the chain rule. So if I want to get dy dx, I just solve for that. But this equation here is equivalent to this one. And so that means over here, I found dy dx. It's this. I'm not sure I'm happy about this, but that's a correct sentence. It's just not particularly helpful to me to have an explicit equation, y equals a function of x, and still end up with an implicit answer. I don't like that. Isn't it? I really don't want to have cosine of y in my answer when my function was just an x. I'd like to turn this back into x's. Plug in the sine inverse, so it would be cosine of sine inverse of x. Oh, that's absolutely unpleasant. I can't quick draw a crying emoji, but you can picture it there. That's horrible. Absolutely horrible. It's not wrong. It's just ugly. So I yes, but no. When I do y equals sine inverse of x, what's y? In terms of trig. We said this right at the beginning. I said that's the angle that gives me the sine. Right? So that's an angle. If y is an angle, I can draw a triangle. This is trig. Let's F calculus. Let's go back to trig for a minute. Y is an angle. And if I'm taking sine of it, I can put it in a right triangle, right? I remember one of the very first things we did in trig is figure out right triangle trigonometry. Sine of y equals x. Where in this triangle would I find that x? Almost. Sine involves two sides of my triangle, Blake. Right, it's the opposite in hypotenuse, but I don't have a hypotenuse. I do? What's my hypotenuse here? Because I can write x as x over 1 opposite over hypotenuse. Pythagoras time. What's this horizontal adjacent side of my triangle? Again, almost. It's the square root of that, right? Because Pythagoras would say that adjacent squared plus opposite squared equals hypotenuse squared. So I solve. I have all three sides of my triangle. What's cosine of y? Square root of 1 minus x squared. Over 1. I don't care about over 1. But now, I have a result for cosine of y that only involves x. I got an explicit formula. Hot damn. Yes, ma'am. Pythagorean theorem. A squared b squared equals c squared. So question mark squared is 1 minus x squared. I take the square root. You're welcome. Yes, ma'am. More questions. I found an explicit version of my derivative. It took a little work. But now I can do the derivative of an inverse function. And if I can do it for sine inverse, I can do it for cosine inverse, tangent inverse, secant inverse, cosecant inverse, cotangent inverse. I can do all of these. Once again, I don't want you to memorize these. Memorizing these sucks. Rederiving them doesn't look like much fun either. So, the hell with it. Page 223, here's a table. Please note, this same table is reproduced on your exam review, as are the derivatives of the trig functions. I don't have to memorize this stuff. The longer I do it, the more I'll remember them. But I got to tell you, out of all of these, I only remember two. And that's the inverse sine and the inverse tangent. The rest of them, if I need to, I get them. But you'll have them. And we get them the same way by doing this inverse implicit derivative. Put a post-it note or a flag or something on this page, page 223. Questions? Remember I said that you had to give this a sign, a value, to get the angle out? And that sign has to be between -1 and 1. What happens if you put a number larger than 1 in here? I don't get a real number. And that means it doesn't work. And if you put in 1, what happens? The square root of 0 is fine. That's 0, but it's 1 over 0. If we look at the graph for the inverse sine function, it's a very small graph. That's the whole thing. And it's only going to work between -1 and 1. And the output is between -π/2 and π/2. But as you get to the end, you're either going straight down or straight up. You have a line whose slope is undefined. 1 over 0 was undefined. You have a vertical tangent line. So this jives with our answer here in terms of the way we think of derivatives as slopes of tangent lines. Questions? So I now have another 6 functions I can play with, which means I can use them in quotient rule, tangent rule, product rule, chain rule, all of these other things I can do now. So I could ask, what is the derivative of sine inverse of x cubed? I don't quite have the right voice today. Chain, chain, chain. It's chain rule time. Sine of ugly junk. Sine inverse. So that means I do the derivative of sine inverse leaving the junk alone, but sine inverse is up there. 1 over square root of 1 minus junk squared. What goes in there is the x cubed. But wait, there's more. The derivative of the junk. I'm perfectly happy to leave that just like that. That makes perfect sense to me. I'm done. But the textbook will probably simplify that and write that as 1 minus x to the 6th on the bottom. And most likely, we'll write it as a single fraction. Questions? All right. Trig functions are not my favorite inverse function. Logarithms are my favorite inverse functions. I'm in the same boat. I don't have to take the derivative of ln of x. But it's an inverse function. So what's the rewritten version of this? Solving for x in terms of y. Say again? I want to get rid of the ln. How do I get rid of an ln? My buddy e. So I get x equals e to the y. That's an implicit equation. Let's use the implicit differentiation and find dy dx here. The derivative of x. The derivative of e to the y. The derivative of e to the stuff is e to the stuff. But wait, there's more. Dy dx. Which means if I want dy dx alone, because my goal was to find dy dx, I divide. And again, I make the same snarky comment. I don't like having a derivative of an explicit function written in implicit terms. How can I get rid of the e to the y and turn it back into stuff involving x? It's up there. E to the y is just an x. The derivative of ln of x is 1 over x. By the way, this actually means something a lot deeper. Because ln doesn't look like it should have anything to do with powers at all. But I just said the derivative of ln of x is x to the minus 1. Somewhere down the line, there's going to be a deeper connection between exponents, logarithms, and powers of x. And that's going to show us something much more important about all of these transcendental functions, functions that aren't polynomials. Keep that in your back pocket somewhere. We'll get back to it. Questions? Again, now this is a brand new rule for me to put in my pocket to keep using in my bag of tricks, pull it out whenever I need it, whenever I see ln. I'm going to say, oh, I know how to take the derivative of ln of x. It's 1 over x. But I have a little bit of a problem. Not a huge problem, just a little one. What is the domain of ln of x? But 1 over x is defined as long as x is not 0. It's defined both for positive x's and for negative x's. What if I did an absolute value? Well, then I'd be allowed to plug in negative numbers, right? I still wouldn't be allowed to plug in 0, but I'd be allowed to plug in negative numbers. The absolute value of x. The absolute value of x when x is positive is just x. But when x is negative, we get the opposite of x, right? You put in -5, you get its opposite. That's minus the negative number. This is really two functions in one. We just defined the derivative of ln of x. How do I do the derivative of ln of minus x? It's ln of stuff. That's my chain rule again. It's not just an x inside those parentheses. I have an outside function, I have an inside function. So I do the derivative of the outside. The derivative of ln of stuff is 1 over stuff. The derivative of the stuff is a -1. Hey, wait a minute. My minus signs are going to cancel out. I got the same damn derivative again. The derivative of ln of absolute value of x is 1 over x, and that works for both positive and negative numbers. Questions? The chain rule shows up a lot in derivatives involving logarithms. What is the derivative of ln of x cubed plus 1? Derivative of ln of stuff is 1 over stuff, then times the derivative of stuff. However, sometimes simply applying the chain rule gives me really messy crap. The derivative of the ln of the square root of x. Yeah. Derivative of ln of stuff is 1 over stuff. But wait, there's more. Square root of x is x to the 1/2. So I write it like that. Wait a minute. A negative power goes in the bottom. And a 1/2 power is a square root. Square root times square root, that's an x. Man, that seems pretty lame. Square root just kind of vanished on me. I'm going to dig back a minute When we did logarithms and exponentials, there were a bunch of properties of logarithms. Just like we had properties of exponents, when you multiply exponents, you add the powers. When you divide exponentials, you subtract the powers. When you take a power of a power, you multiply them together. A logarithm is a fancy name for a power. Square root's a 1/2 power. When I take a power of a power, I multiply those powers together. The logarithm is asking me about powers. This is what power and a power. Rules for logarithms say, what can I do with that 1/2? Can move it out in front and multiply by it. What's the derivative of ln of x? 1/2 1 over x. Isn't that what I got here? Son of a... As long as I am willing to play with the rules for logarithms, I can make derivatives of logarithmic expressions much easier. I want you to imagine for a moment that we start this the same way we did up here. The derivative of ln of stuff is 1 over stuff. First of all, I'm then going to have 1 over ugly fraction. Then I need the derivative of the stuff, which is a quotient rule with a chain rule inside it. I think I'd rather hit myself in the head with a book. And this sucker's big. Let's not do that. I'm going to take the rules of logarithms and go to town. I'm dividing. When I'm dividing powers, what do I do with them? So when I'm dividing logarithms, I subtract the corresponding logarithms. Now, I can play the same square root trick we just played up above. I can write this as a 1/2 power. And then my power pops out front. Because multiplying power, a power of a power means it gets multiplied. Now, there's still some chain rule involved. Because it's not ln of x, it's ln of stuff. But in this case, the stuff has really nice derivatives. What's the derivative of x plus 1? What's the derivative of x minus 2? That makes my life a lot easier, doesn't it? So when I start doing the derivative, I really do the derivative of this stuff. 1 over stuff times the derivative of stuff, which is 1, minus 1/2. 1 over stuff times the derivative of stuff, which is 1. I'm done. If you really want, you can get a common denominator. No. It said on the exam, don't simplify. I'm not going to do that. Questions? Yes, ma'am. Here? That's ln. It's not 1 minus, I promise, with my shitty handwriting. I apologize. Whoops. We used the chain rule to work with bases for exponents that weren't e, because we could change the base. I don't know about you, but I'm a math geek. I love base e. If you're a chemist, you want to work in base 10. pH. If you're a physicist, sound, decibels, light, they're all powers of 10. Working in base e sucks. So what if I wanted to work with logarithm log? Well, that's common logarithm. That's the base of 10. I have not done any sort of derivative for anything other than e. So let's change the base. There's a formula for that. Find it for me. The internet is your friend. Logarithm change of base formula. Hold that thought. I'm ready. Now I chose to use, for your base d, I chose to use e. So logarithm base e is ln. So a log in any base can be changed to ln's, which means this log base 10 of x becomes ln of x over ln of b. But ln of b is a constant. Oh, wait a minute. B. B is 10 here. Put a 10 there. ln of 10 is a number. Grab your calculator. What's ln of 10? Didn't we do this just the other day? Doing 10 to the x? Pretty sure we had this number before. It's 2 and change. But that means this is 1 over a number. So the derivative of log x is the same as the derivative of 1 over a number times ln of x. This is a constant. When you take the derivative of something with a constant in it, what happens to the constant? Say again. Only goes away if the constant is alone. This constant's being multiplied. Its coefficient, it just stays there, which means I get 1 over ln of 10 times 1 over x. Was there anything magical about the number 10 in this problem? Nope. This formula applies to any base. If you're in computer science, your favorite logarithm is going to be log base 2, the log binary. Well, then I'd have 1 over ln of 2 instead of 1 over ln of 10. If for some reason you're using a really weird base, I don't know, 27 over 49. Came up as a base in one of the application problems in one of my other classes. Great. Now I'll get 1 over ln of 27 over 49. It literally doesn't matter what base you're working in. I am going to continue to work in base E as often as I can get away with it. But in general, the derivative of log base B of x is 1 over ln of b times 1 over x. As long as b is any number bigger than 0 except 1. I love my change of formulas. Questions? When I learned how to do implicit derivatives, I was able to then use that to do all of this. But it is the properties of logarithms that allow me to make these derivatives so much simpler. So let's take a really weird ass function. If this was x to a number, then I'd use the power rule. If this was number to the x, I'd use the exponential idea. But they're both x's. If I can't change it to a logarithm, that right hand side is just a power, right? Let me write that left hand side as y. Just change it to a letter for the moment so I can keep track of it better. What if instead of rewriting this equation, I did something that I remember back in algebra? When I was trying to solve weird equations involving exponentials, I would try and get rid of the exponential part. I would do it not by rewriting all the time, but sometimes I would just say, put an ln in. The ln function is 1 to 1. So if I take the ln of the left side, I can take the ln of the right side. That's an equivalent equation. ln of y is equal to ln of x to the x. Now I can see from some of your faces, you're like, what the fuck is this going to do for me? This is now messier, uglier, and less useful. Why are you doing this stupid crap? I have a power inside a logarithm. I can put it out front. Now that right-hand side is a product. I can use the product rule if I take the derivative. But the left-hand side is now messier because the left-hand side is in terms of y, not x. And that means rattle, 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 rattle. I'm going to do the derivative implicitly. I'm going to use the chain rule. So on the left side, when I take the derivative here, the derivative ln of stuff is 1 over stuff. But wait, there's more. My derivative from the chain rule, dy dx, equals right-hand side. Product rule. Derivative of x is 1 times ln of x plus x times derivative of ln of x. Hey, that's a 1 over there on the end. You'll notice that's why I have parentheses around the ln of x part, so that I know that that plus 1 is outside. But over here, I still have 1 over y dy dx, and my goal is to find dy dx, so I need to move the 1 over y. So I get dy dx is y times ln of x plus 1. Ew. I started with an explicit function. I want to end with an explicit derivative. What's y? Ta-da! This idea of inserting a logarithm and then taking the derivative is called logarithmic differentiation. And it is most useful in places where I have either functions of x as both base and exponent, this one tight, or where I have large, complicated, ugly looking chain rule problems. If I ask you to find the derivative of this before you throw something at me, you would say, all right, wait a minute, that's ugly to the 1/4. So I can do the chain rule. 1/4 ugly to the -3/4, and then the derivative of the ugly, which is the quotient rule. Bleh. It works. Don't get me wrong. That works. The derivative is going to have all of this jump to the -3/4 power. Trying to work with that to simplify it is going to suck. Let's cheat. Instead of taking the derivative the way it is written, put an ln on both sides. It doesn't really matter. Because what I'm going to do is I'm going to treat it like this, and that's a power, isn't it? What do I do with that 1/4 power? Wait a minute. I've got the logarithm of something being divided. What was that, Jordan? Oh, sorry. Subtract. Division becomes subtraction. But I'm the 1/4 is by the whole thing, right? It's a quarter of the subtraction of the whole thing. Well, doing the derivative here is a lot easier because the chain rules are a lot simpler. So let's do this derivative. What do I get on the left-hand side? One over y times dy dx. And over on the right, derivative of ln of stuff is 1 over stuff times the derivative of the stuff. Oop, I made a copy error. I forgot to write the ln there. Can't take the derivative of an ln if I don't have an ln there. Ln of stuff is 1 over stuff times the derivative of the stuff. If you really want, you can simplify a little bit because I got a 2 on the top and a 4 on the bottom in both of these fractions. But my goal is to get dy dx. So what do I have to do? Multiply by the y. I'm not going to write it as y because it was an explicit function to begin with. I'm going to write back in this instead of y. And there's my derivative. Remember when I showed you the chain rule? And I said there was this monstrous, ugly example that I had from 11 layers deep or something like that. If we go back and look carefully, we see that the function involved at two different places. X to the x. So in order to do this chain rule version, which is why we didn't actually do it, we just counted layers, I needed this trick. I even had an ln and an arctangent in here. So I couldn't have done this derivative until today using my chain rule, but I can count the layers in it regardless. And that's why it was just an example for counting the layers in the chain rule rather than doing the chain rule. Questions? If you did this problem the chain rule way, you would get the exact same answer. It's just uglier. 1/4 junk to the -3/4 and all the quotient rule, and then you got to keep. No, I don't like doing this. So now the question is, now that I can do all these different derivatives, what do I do with them? Let's start putting this into situations you are already in. I want to know, where do I see my derivatives in the other classes I'm going to take? So, chemistry, biology, physics, electricity, social sciences, business, where do these show up? That's what we're going to do for the next couple of days. I will see you all Friday. Have a wonderful day.